Let me ask you something. Have you ever designed a network that looked perfect in theory, but the moment you added redundant links, everything started behaving strangely? The network slowed down. Traffic flooded everywhere. Nothing made sense. If you've seen that, or you're worried you might, you're in the right place. In this video, we're going to understand why this happens, and how Spanning Tree Protocol keeps Layer 2 networks stable and loop-free. Welcome to Bluehat Cybersec Academy. Imagine building a network with multiple switches. You add extra links for redundancy, because, redundancy is good. But suddenly, the network slows down, then it crashes. That's not bad hardware, that's actually a Layer 2 loop. And this is exactly why Spanning Tree Protocol, or STP, exists. The core problem: why Layer 2 loops are dangerous. Here's the problem. Ethernet networks just don't handle loops well. In fact, they don't handle them at all. At Layer 2, frames don't have a hop limit. Broadcast traffic is flooded everywhere, and switches forward frames blindly. So, when a loop exists, traffic just keeps circulating. Forever. This leads to broadcast storms, MAC address table instability, duplicate frames, and eventually, a full network outage. Routing protocols can stop loops, Ethernet switching cannot, and that's why STP is needed. Now, STP doesn't remove redundancy from the network. Instead, it controls it. It looks at the physical topology and then builds a logical, loop-free path through it. Those extra links you added aren't removed. They're simply placed on standby. And if the active path ever fails, STP brings a backup link online. Quietly, automatically. So what's actually happening behind the scenes? First, switches exchange special messages called BPDUs. These messages allow all the switches to agree on the structure of the network. From there, one switch is elected as the root bridge. Every other switch then calculates the best path to reach that route. Redundant paths are identified and blocked. And what remains is one clean, loop-free topology. It's a simple idea, with a very powerful result. Now let's talk about that root bridge for a moment. The root bridge is the center of the entire STP topology. Every switch measures its distance to this device, which means choosing the right root bridge really matters. Each switch has something called a Bridge ID. That ID is made up of two things: a priority value and a MAC address. STP follows two very clear rules. The switch with the lowest priority wins. If there's a tie, the switch with the lowest MAC address wins. By default, all switches have the same priority. And that means the root bridge could be chosen randomly, which is usually not what you want. That's why, in real networks, engineers manually decide where the root bridge should live. Most of the time, it's a core switch or a distribution layer switch. This keeps traffic flowing efficiently and prevents strange paths through access switches. Once the root bridge is selected, every single port in the network gets a specific role. Each non-root switch chooses one root port, the port with the best path toward the root bridge. On every network segment, there's also a designated port. That's the port responsible for forwarding traffic for that segment. Any remaining redundant ports become blocking ports. These ports aren't broken, they're not unused, they're just waiting. If the topology changes, they're ready to step in. Now, in classic STP, ports don't jump straight into forwarding mode. They move through several states. First, blocking, where no traffic is allowed. Then listening, where STP calculations are happening. Then learning, where the MAC address table is built. And finally, forwarding, where traffic flows normally. This entire process can take anywhere from 30 to 50 seconds. And that brings us to some very common STP issues. One of the biggest problems with classic STP is slow convergence. If a link fails, users may experience noticeable delays or packet loss. That's why most modern networks use faster versions like RSTP or Rapid PVST+. Same concept, much faster recovery. Another common issue is having the root bridge in the wrong place. When that happens, traffic takes inefficient paths and overall performance drops. Most of the time, this happens simply because priorities were never configured. The fix is straightforward. Manually define the root bridge and set a secondary route as a backup. Sometimes, engineers also run into unexpected blocking. A link that was supposed to carry traffic ends up blocked instead. This might be due to a higher path cost, a different port priority, or even mismatched STP versions. That's why, visibility really matters. Commands like show spanning tree tell you exactly why a port is blocked. Then there are PortFast and BPDU Guard issues. PortFast is designed to speed up ports connected to end devices. But if someone accidentally connects a switch to one of those ports, STP suddenly sees BPDUs where it shouldn't. The result? The port shuts down instantly. It's a protection mechanism, but one that can, honestly, surprise engineers if they're not expecting it. Another thing to watch for is frequent topology changes. Too many STP changes can flush MAC tables and temporarily interrupt traffic. Common causes include flapping links, bad cables, or misconfigured trunk ports. Stability really matters here. Now, even though STP is still incredibly important, it's no longer the only tool in the toolbox. Modern networks often rely on faster protocols like RSTP or MSTP. They use Ether channel to avoid blocking links altogether. And, many designs push routing closer to the access layer to reduce reliance on layer 2. Even so, if you work with Ethernet networks, you must understand STP. Because while it may not be exciting, it's one of the most important protocols keeping your network alive. Without STP, layer 2 networks fall apart. It prevents loops, it preserves redundancy, and it keeps traffic flowing. No STP means broadcast storms, network instability, and, honestly, very angry users. STP is quiet, it's reliable, and it's absolutely essential. And that's the real takeaway here. Spanning tree protocol may not be flashy, but it's one of the biggest reasons your network stays online when things go wrong. Thanks for learning with Bluehat Cybersec Academy. If this video added value to your day, give it a like, share it with someone who's learning networking or cybersecurity, and subscribe for more clear, practical breakdowns like this. Drop a comment below. I'd love to hear how STP has shown up in your own network experiences. Until next time, stay curious, stay secure, and keep building smarter networks.